Okay, hello, my name is Titus Dudden. I'm part of the 3110 computer engineering course, and I'm going to be going through testing all of my different devices that I had to code for project 1. So for my first project in the list was a 1-bit and 3-gate. As you can see, here's the code here down below, and this is a waveform of the code being tested through a test bench. As you can see, whenever all of the values are high, the output is 1. So it's doing what we want. Whenever any of them are low, it's 0. So the test bench is proving. And if we go here, here is what the RTL viewer has decided it should look like, which looks pretty solid to me. I'm content with that. And if we move over here to the hardware testing, we have an LED that is high, showing that all three are high. So the output would be 1, and if we drop any of the outputs, it drops to 0. Over here on the oscilloscope, we have the time delay between the initial input, which in the block diagram would, let's see, right here. So we're determining the time delay between this F1 output and this F0 output, saying that the time delay between the initial input and the time that it took to actually do the process is about, as you can see, 200 nanoseconds. And that wraps it up for the AND3 circuit. Hello again, this is my second circuit testing. So what we're doing now is we're doing the 2-bit NAND 3, where we have 3 2-bit inputs and 1 2-bit output. As you can see, here's the code, and here is a waveform of said circuit. And as you can see, for this test in particular, what it is these bits are being ANDed together, whereas the 1 doesn't really matter. Then they NAND, so therefore they're 1. These are all zeros, it does the same. And if we move to Quartus, here's the block diagram I'm using for the hardware test. And assuming that I compiled it correctly, we can go to Netlist Viewer and RTL Viewer, and this shows us what the compiler is believing it should look like, which looks how it should, in my opinion. And then we will move to the hardware test, where, as you can see, each switch is correspondent to a bit of information. So if all of these are 0, they are NANDed then to 1. If one of them's 1, it doesn't matter. But then if all of them are 1, then it kicks off. Same thing for this side. And if we move to the oscilloscope, this is the observed time delay between the transitions of the input and the output. So as you can see, there's a time delay of 20 nanoseconds. And that's it for this circuit. Okay, I'm back with circuit 3, which is my 1-bit input XOR 3, where I have the code here for the circuit. A XOR B XOR C XOR is equal to F. And here is the waveform for it, where you can see that if any input, or well, not any input, but if one input is 1, then the output is 1. But in any case where more than one input is 1, then the output is 0. And if we move, I think, yeah, that's all I gotta show. But I can show the Quartus first, because that feels a little better to me. And then here's the block diagram, where we have all 3 inputs and an output, an LED output, and then another output, these 2 to determine time delay. And then we have, oh, I got rid of it, tools, and then we'll go to Netlist Viewers, RTL Viewer. And this is what it thinks it should look like, and I also think that's what it should look like. So I'm in agreement. And if we move over to the hardware test, we can see that if any of the 1 inputs is on, then the LED is high. But if we have 2 that are high, or all 3 that are high, then we're good. Fun stuff. And now if we move right here, then we can see that there is a time delay of 6 nanoseconds, which is very small, and I may have approximated my numbers, but we're gonna go with it. And then that's it for the circuit. Okay, this is the next circuit. This is the 2-bit NAND 3 component, which is the same thing, but rather than just using a simple equation, but with 2 bits arrays, I'm using a 1-bit, and this is the code for it. And I'm stringing it together using port forwarding and wire outputs and arrays for the inputs and outputs, and I am stringing a bunch of values together to do the same thing. And the goal of this is to observe time delay, see if this does anything differently. And as you can see, the waveform for the example that I've chosen, which is where the yellow line is, all of the values are 1, which then the bit is 0, and all of the values are 0, which then the bit is then 1. And if we move on to Quartus, we can see this is the block diagram where I have the bit outputs, the LEDs, and then the bit input as an output, so that we can just observe the time delay from the beginning of this block to the end of this block. And up here I have the RTL viewer, which looks, to my memory, if my memory is correct, the same as the non-component 2-bit NAND. This says NAND 2, it's supposed to be NAND 3. I had a little bit of a labeling issue, so ignore that. And if we move on to the hardware testing, then we can see that all of these are high, so they're low. If I change any bit down to 0, then it correspondingly goes high. If I do the same thing for this bit, it does so. If I drop any of these bits, it follows. And then over here, we can see the time delay on the oscilloscope reading 20 nanoseconds. And my memory is not good enough to know if this is the same or greater than the non-component form, but you'll know if you read the PDF. And that's it for this circuit. Okay, this is the behavioral circuit for the AND3. As you can see, this is the code down here. I have used an outside of an always statement if else script right here, saying that if basically saying if all the values are 1, then this is 1, else then this is 0. And my test bench decided not to work, so I just forced some values for a simple test bench showing that when all the values are 1, it's 1, and then if in a different instance, if any of them are low, then the output is low. So it's working how we want it to. And if we go to Quartus, if it'll let me, then we've got the block here where we have the output after the computation, an output for pre-computation, and then an LED output. So the same as all the other blocks. And then if we go to our RTL viewer, then it gives us the behavioral block, or what I think it should look like, which I agree with it. And that's all I need to show you on Quartus. So then we'll move on to the hardware test, where if all of them are high, then we're good. If any of them are low, then the LED is off. So a three input AND gate. And over here on the oscilloscope, we have the time delay, which looks like it is about 60 nanoseconds. So all around, these are all the data points, and that's everything we need to hit for this one. Okay, for our next circuit, we have the 3-bit adder in equation form, which is just, we have 2 3-bit inputs, which then are being added together to a 4-bit output to work with possible overflow. And I've chosen for the waveform to have an example of 101 plus 100, which then results in an output of 1001. So we can see that the 4-bit output is functioning as desired, which works as an overflow in this case. And then if we move to Quartus, we can see this is the block where we have the output, the computational output, LED outputs, and then the input as an output to determine time delay. And we can see the RTL viewer, which is similar, where it's just recognizing this all as one big block, since it's just a equation form effectively. So there's nothing complicated that it's thinking is happening. And if we move to the hardware test, we can see that if I add 1 and 1, I get 2. And if I add 2 and 2, I get 4. And if I add all of these plus 1, there's that 1 carry bit right there. So we have that set up, and that's working properly. Over here we have the time delay, which seems to be negative 60 nanoseconds or 60 nanoseconds in magnitude. And that's it for this circuit. Okay, for our next circuit, we have the 3-bit adder in component form, which is just using a bunch of port forwarding to a single full adder, which this is the code for the component 3-bit adder. This is the code for the full adder that was used. As you can see, it adds them together plus the CN, and it takes the top bit as C out and then the remaining 3 LSBs as S. And then we use those, including a multi-bit wire, and just carry them through all of the different ports of the adders. And then we can see that I chose a similar example as the previous one, where it's adding 110 and 011, and in this case the S out is 001, and the C out is the overflow bit that would move to a next to another full adder, but in this case it's just the C out output. And if we move over to Quartus, this is the block used, which this one was a little bit more ambiguous. We have CN and then our 3-bit inputs, and then we have a 3-bit output assigned to LEDs, and then the carry output, which is not used on the oscilloscope for time delay, so it's just an LED output, and then the inputs as outputs, which again, these are used to determine time delay between the input and the output of the computation. And if I go here and I go to the component, where is it? Double tap this and go to Tools, Netlist Viewers, and RTL Viewer. You can see this is what this looks like, but that's not what I was getting earlier. So what I'm going to do is I'm going to set this as the top level, and I'm going to recompile it and see if I can get what it was giving me earlier, where it had 3 blocks being strung together, which looked like more fun to me. So then we're gonna go here, we're gonna go to Tools, and then Netlist Viewers, RTL. Let's see if it gives us, yes, it gives us the fun RTL viewer, where it has all 3 blocks being strung together to a C output and then a 3-bit output. I think this looks like way more fun. And then if we move over here, it works the same, where if we have a carry in bit, it carries in. If we have 3 bits, it's 3 bits. If we add 1, then we have this right here. If we add a carry in, it adds 1 bit. I don't know why all these LEDs are lighting up, but that's just the charm of Altera. And the board is working as it should. And then over here on the oscilloscope, we have the time delay, which looks like about 120 nanoseconds. And that is everything for the circuit. Okay, this is the final circuit recording. This will be the 2-bit adder subtractor, which in similarity to some of the 3-bit adders that I had, I'm using an overflow and an S, where the output is if a 3rd bit is thrown into the mix, then that is pulled off the S as an overflow. And it's saying that if the mode is 0, it adds, and if the mode is high, then it subtracts the bits, which can be shown here. And in this example, the mode is high, so it's subtracting. So it's taking 001 and 00 and subtracting 01, which then results in 11 and an overflow of 1. So we know something went terribly wrong here. And then there are more examples further into this. And then I will move to Quartus, if it will let me. And this is the block diagram that we have here. So the 2-bit inputs with the mode input, the overflow output, 2-bit output, and LEDs, and the 2-bit input as an output, again, to determine time delay on the oscilloscope. And I have the RTL viewer here for the verilog, and it is a lot more messy than all of the other ones, which have effectively just been blocks. But it's basically just saying that these bits are being added, these bits are being added, and then they're getting thrown into a mux with the mode, which then determines what is actually happening here. And then we have a bus where it pulls the overflow and it pulls the remaining 2 least significant bits. And if we go over here to the hardware test on the board, we can see that we can add 1, we can have 2, and then, or sorry, 3, and then add 1 more, which then triggers the overflow indicator right here. And then we can, let's see, I believe this was mode. So if we have 0 and we subtract 1 from it, then we have 1 with an overflow. If we have 1 and we subtract 1, we get nothing. So it's working as desired. And then over here, we have the observed time delay, which was about 120 nanoseconds. And that is everything for this project. These are all the circuits, and project 1 is completed.